Hello everyone, glad that you could virtually join my presentation on the application of surrogate models for performance-based evaluation of multi-story concrete buildings at early design. I will first introduce the problem that this research addresses, which is how we can leverage surrogate models for a risk-informed early seismic design. Next, I will talk about developing suitable performance inventories for this purpose. After that, I will discuss the process to create efficient and generalizable surrogate models. And finally, I will show the results and finish the presentation with key points that we will discuss. Requires holistic design methods that can link buildings' physical characteristics to their life cycle performance. Early design is the first step in a holistic design process, which defines a design problem and introduces and tests different ideas to address the problem iteratively. For buildings, early design is the most critical stage to shape performance because the influence of decisions such as subsystem and material selection is the highest at the lowest cost. A conventional early design follows the designer's familiar domain of knowledge and is constrained by their cognitive biases. Therefore, often only limited alternatives are evaluated and high performing alternatives are missed. Now, computational tools can supplement the early design process and resolve these shortcomings. A particularly useful computational tool is the performance based engineering or PBE framework. PBE is a quantitative method to evaluate the impact of natural hazards on the built environment. The generic PBE comprises independent probabilistic modules linked to intermediate variables. While the number of these modules varies for different hazards, typically there is a hazard analysis module providing probabilistic description of hazard likelihood and intensity, a system analysis module that evaluates the system under the hazard, and a loss module that translates system damage measures to some decision-making variables such as repair costs or loss of functionality. While PBE has been widely used as a performance evaluation method, it has not yet been implemented in early stages of design. This is mainly because PBE assessments are time and effort intensive, while the dynamic nature of early design frequently changes simulation input. Surrogate modeling offers an efficient solution to substitute intensive simulations of PBE with low-cost mathematical metamodels, allowing for PBE to be implemented in early design. As such, this presentation introduces surrogate modeling suitable for early seismic design of multi-story concrete frames. The first step for surrogate modeling is to provide enough data that is suitable for model training and validation. As shown here, a pseudo-directional workflow is devised that obtains seismic performance in terms of structural seismic repair costs for an inventory of 720 mid-rise concrete office buildings. The workflow comprises three modules. First, the Latin hypercube sample is used to sample basic parameters that can represent the topology variation of this class of buildings. The second module then uses sample geometry and section design data to auto-generate nonlinear finite element models in an open source platform called OpenSeas, and then subject them to 80 site-specific grand motions, resulting in more than 72,000 simulations. The third module post-processes the results of the second module and combines them with hazard and construction data to derive a structural repair cost. To make models suitable for early design, we're using very crude parameters that are estimable at this stage. These parameters fall into two categories of topology and design. In topology, building height, building dimensions, and area are included. Whereas in the design category, parameters such as weight and average design informations are taken. I should mention that all these input features are derived from the developed performance inventory. Following the best practices of data science, a machine learning pipeline is built in Python language to relate input features to structural seismic laws. Data is split into training and testing sets so that we train our models on one set and evaluate their accuracy on a different set, ensuring their generalizability. To select features, a subset from three criteria are compared: F-value statistical testing, mutual gain, and a recursive feature selection algorithm. For each machine learning algorithm, careful hypertuning is carried out to find optimal parameters of the model. The tuning starts with a randomized search scheme to find bounds on hyperparameters, where a grid search narrows down the range to final values. In both search algorithms, threefold cross-validation is performed to avoid overfitting, where a k-fold cross-validation splits a set to k subsets of equal size and trains on k-1 sets, and then tests on the k set and repeat this process k times. Finally, the tuned models are tested on the testing dataset, and the model accuracy is measured based on several criteria such as root mean square error or RMSE and adjusted R square. Now, RMSE is a criterion of true error because it calculates on average how far predictions are from actual data, whereas adjusted R square measures the amount of response variance explained by model penalized by extra features. Five algorithms are compared in the pipeline to represent a wide range of machine learning tools with respect to flexibility interpretability trade-off. As models become more flexible with data, their interpretation becomes harder. From least square methods with high interpretation, multiple regression is chosen, whereas random forest and extreme gradient boostings are chosen as a bit of a middle ground. And finally, support vector machines and k-nearest neighbors represent low interpretable models. Now, multiple linear regression, or MLR, assumes that the response is linearly related to multiple features. The coefficient of the model are then obtained by minimizing the sum of square residuals. Random forest uses the bagging concept where the average of a large number of noisy models, here decision trees, from resampling training data is expected to result in an unbiased model. Gradient boosting methods rely on boosting approach in which weak models with low bias and high variance are used in a stage-wise fashion to retrain the trained models at each iteration. Now, extreme gradient boosting uses a more regularized loss function to limit overfitting compared to other implementation of gradient boosting methods. Support vector machines find the optimal hyperplane in the input space that deviate at a maximum of epsilon from the decision boundary lines. And finally, k-nearest neighbor algorithm predict response for predictor by locating the n nearest points in the input space and then averaging all the corresponding responses. So which model performs the best? First, based on overall high R-square values, we can see that the pipeline trains surrogate models with reasonable accuracy for this class of buildings. Overall, support vector machines and extreme gradient boosting provides the best accuracy measures, whereas support vector regressions slightly outperform extreme gradient boostings. K-nearest neighbors show low RMSE for training, whereas a relatively higher RMSE for testing indicate overfitting. This means that the k-nearest neighbors will perform poorly for a new dataset. Random forest shows a high standard deviation of adjusted R-square, which means that the model is quite sensitive to new data, providing inconsistent accuracy. Lastly, while multiple linear regression has a reasonable adjusted R-square, it shows high RMSE. One last observation is that height, floor area, and average beam section and the weight-related parameter are selected in all the best models. Important question is how prediction varies based on uncertainty in the input parameters. Therefore, variance-based sensitivity assessment is performed on the best machine learning models. In this method, response variance is decomposed into partial variances, and first order and total effect Sobol indices are calculated as the ratios of these partial variances to the total variance, where any parameter with a Sobol index above 0.05 is deemed influential. For support vector machines, the uncertainty in floor area and average beam section size dominate the first order and total effect on structural loss variance. While the first order impacts of other features such as reinforcement ratio and height is not significant, their total impact is considerable and on a similar magnitude, which indicates that the model prediction variance is impacted by these parameters' interactions. On the other hand, for XGB, floor area, total building weight, and building dimension in the direction perpendicular to the analyzed frame dominate both the main and total effect. Whereas the impact of design parameters such as beam sections and column reinforcement ratio on prediction variance is negligible. So three main takeaways of this presentation are that support vector machines and extreme gradient boostings are able to map a structural loss to building topology and design. And for the studied inventory, support vector machines and extreme gradient boosting showed an average R square of 95 and 90% on the test data. And also the variation loss prediction from extreme gradient boosting and support vector machines are sensitive to different predictors, where XGB is mostly dominated by topological parameters, whereas support vector machine is more governed by design related parameters.